New everyone, and this time in this episode, we're finally talking about logic gates.
Yes, logic gates, a very interesting topic. First, we gotta talk about something important about logic gates. What's the purpose of them? Why are they used? That's a great question. Purpose of logic gates is simple as this. They're used to perform logical functions in digital circuits used by electronics that use memory processing. Some basic functions they use is pretty much basic arithmetic actions like adding, subtracting, multiply, dividing. They're mostly practically used a lot for mathematical applications. So now the big question is going to ask, okay, now you know the purpose, then where, what piece of technology are they used? Well, simply anything that has memory processing, which it goes down to your simple smartphone that you always use every day, your computers, your tablets, even like MP3 players, just anything that has any memory processing within its CPU or whatever, logic gates is always used in there.
And just in case, logic gates can also be treated as a function as well. So if you haven't watched the episode of us talking about functions, go take a look at that and then come back over here, because in this case, when you just look at a single logic gate, it really acts like a function. It takes some input and then finally give you an output. So in this case, before knowing logic gates, we need to know a certain data type. Now in this case, there are many data types. There are like integers, they can be letters, they can be numbers or positions or whatsoever. Now in this case, we need to know something called a Boolean. So a Boolean has only two values, and these two values are the opposite of each other. So these Booleans do not exactly has a fixed names. Like if you go for numbers, it's not like if you go for numbers, it's always 0, 1, 2, 3, 4, 5, 6 or whatsoever. And then if you go for color, it can be red, green, blue, yellow, whatsoever. But in this case, Boolean, as long as the two values are the opposites of each other, you're good to go. However, by convention, everyone agrees that the two values that Boolean has is true and false. Now, as you can see, these are two abstracted ideas, but they're opposed of each other. So it can be anything. Like for example, it can be on or off, it can be up or down, it can be right or left. As long as these two ideas are the opposite of each other, then you're good to go.
And so for technology sense, for logic gate sense, we use 0 and 1 to make visual representation. To make it easier between 0 and 1s, we'll use this beautiful device right here. So when a input has the value 0, as shown here with all these 4 light bulbs, there's no current going through any of them. As soon as I press this button, the light turns on, showing there is now current going through, now displaying a value of 1. This is the best visual representation of Boolean used in electricity. 0 for off, 1 for on.
Or another way to see it is 0 for no current or no voltage, and then 1 is the other way around. So yeah, we have that.
Alright, so the other important piece of logic gates that we need to know before we talk about logic gates is a very important electrical device called a transistor. Now you ask yourself, what the hell? What is a transistor? What is it? Simply, a transistor is a semiconductor device that controls the flow of electrical current and voltage in a electrical circuit. So that it helps us monitor pretty much what goes in and what goes out of a simple circuit. So a transistor is composed of three important parts: the emitter, the base, and the collector. And each part is important. The collector, you can see the collector as pretty much the source of the power, and then it flows outwards to the emitter. And the base itself is kind of like the control switch. It determines if it goes on, if the electrical current stays on or off. That's the base. And we have other examples to help visualize, what this complicated subject is.
So for example, like go to your kitchen sink whatsoever, and then normally you just like turn on the sink, you just like pull out your hand and then put it on the handle and then you just yoink it, and then there you go, you have water. So in this case, the main example would be something the collector would be, let's say, maybe like your water source or pipe or whatsoever. And then in this case, I activate the base. In this case, I yoink the handle. And then out comes the water from your sink. In this case, that would be the emitter.
And so for electrical sense, if you want to use electrical sense, take this light bulb. We know how light bulbs works. You go to pretty much a light switch, pretty much the collector is pretty much where where your electricity is coming from, and then the base will be the light switch turning on and off, and of course the emitter will be this light bulb, and then when you turn on the light switch, the light bulb turns on, casting the light all around the room where it is, and then when you turn off the light switch, the light bulb just turns off, and there'll be no more light. So it's simply on and off, just like a light switch.
So just in case, transistors, or in this case logic gates, also works just like functions, because just like I said it before, like logic gates, they take inputs and then based on the different input it has, and it will just give you different outputs in this case. So in this case, if you haven't watched episode 1 of the series, which is like, it's just me talking about functions, you can go take a look at it and then come back over here when you're ready.
So we need a way to display the values and pretty much compute the values of what logic gates in a circuit will be. And we have that special little table, we could say, called the truth table. So you wonder, what's the truth table, you ask? So a truth table is simply pretty much a chart that displays all the inputs that are used in the circuit and the output used in the circuit, and it shows all combinations of inputs and outputs that circuit will output with the correct logic gates. A better explanation is it grabs all possible combinations from all the inputs from all the different logic gates, and it breaks down into individual components, which allows us to give us the nice simple output.
First, we have the NOT gate, which is the simplest gate. It takes one input and it flips the signal, meaning turns zeros into 1, turns 1 into 0. It's extremely simple, but important. Next, we have the OR gate. In order for it to give you a 1, A or B has to be 1, or both, doesn't matter. If both A and B are 0, then it will give you a 0. This is the AND gate. Both inputs needs to be a 1 in order to output a 1, otherwise 0. Those gates mentioned earlier, they can be connected back to back and end up with some new gates. A NAND gate is an AND gate then followed by another NOT gate. NOR gate is just a simple OR gate, then followed by a NOT gate. The exclusive OR gate is my personal favorite. If the inputs are different, then it gives you a 1. If they are the same, it gives you a 0. A not exclusive OR gate is just an XOR gate followed by a NOT gate.
So in this case, theoretically speaking, any logic gate that take 2 inputs, there are 16 of them, and theoretically all of them can be made. So for example, if we just take a look at logic gate, what I would call logic gate number 12, or I would call it 0011, basically it's actually just read what is the first input, like in this case, look what is A, and then return A. So if A is 0, return 0. If A is 1, give it a 1 whatsoever. And then based on this idea, if you just go through all the 16 possible gates, you can actually categorize all the previous logic gates we have talked about earlier can be categorized into these 16 logic gates. And technically speaking, if you have, let's say, 3 inputs, that will give you 2 to the power of 8 possible logic gates or logics in this case. But by using the same idea, you can actually force some of them and you'll end up with the logic you want. Like for example, let's just say specifically you exactly only one. Like let's just say we have our inputs A, B, and C, and then let's just say you exactly only one. When A is 0, B is 1, and C is 0, under this condition, it will only output a 1, or otherwise output 0. The way you can do it is just check, hey, grab A, and then you flip it because you want it to be 0, and then now you flip it, now you get a 1 by using a NOT gate. And then B, hey, B is already 1, just let it stay there. C in this case, it's a, well, in this case, we want a 0. So when it's a 0, we want to flip it into a true. Now, in this case, we have the flipped A, the normal B, and then the flipped C. And then afterwards, we just need to AND gate all of this thing. And then basically, if any one of them just like, if any of the inputs just like break any of this, it will just output 0, or otherwise, if all the inputs fulfills the requirements we need, in this case 0, 1, 0, then it will output a 1. So technically speaking, it can theoretically make as many logic gates, like as complicated as you want. It's going to look extremely bulky and all that stuff. So yeah.
If you still remember that we said at the beginning of the video, we did say something like logic gates can do arithmetic stuff. Here is one of the examples. Say we want to add 2 numbers together. We will add the numbers digits by digits. In this case, we are dealing with binary digits, so the possible digits are 0 and 1, which fits the current situation we have. Like, if we have a current, then it's 1. If we don't have a current, it's 0. So it's perfect. What is showing on the screen here is a full adder. It has 3 inputs, the digit from the first number and the digit from the second number. And sometimes it is possible to have carries from the previous digit, like the part where back in base 10, when the digit adds up to 10, we will carry it to the next place, and the next place will have to catch it. It is the same idea over here. It is just, instead of carrying 10, we are carrying 2 in this case. and the full adder has two outputs, one for the sum, one for the possible carry that will bring it to the next digit. Now, if all digits are 0, then the sum is 0, and the carry is also 0. If all inputs adds up to 1, then the sum is 1, and there's no carry at all, so carry is 0. If all inputs adds up to 2, this means we have to carry the 2 to the next digit, and then the sum will become 0. So here our sum will be 0, and our carry will be 1. And if all inputs are on, meaning it adds up to 10, like the digit from the first number is 1, the digit from the second number is also 1, and then we also have a carry, then what we will do here is we will have a carry, so carry is 1, and then we also have a sum as well, so the sum will be 1 as well. On the screen, you can see both of us are going through all 8 possible input combinations. But you might asking, hey, why 8 possible input combinations? This actually hints you in one of the previous episodes, Steve and I were talking about binary. If you haven't watched that video yet, go take a look at it and then come back. The concept is quite important when it comes to electronic things like this. So far we only have the signal flowing from one direction to another. But what will happen when we wrap the signal back to the front? Things will become interesting. One mechanism uses this idea, which is the RS latch, or aka set reset latch. Now, by convention, RS latch starts with both inputs as 0 and its output as 0. Now, when we give the S input a pulse like a shock, like turn it on and then off quickly, the output will become 1. And no matter how we mess with S, like how many pulse we gave it, or we let it stay turned on whatsoever, the output stays at 1 until we send a pulse to R, or meaning to reset the system back to 0. And no matter how we messed with R, meaning turn it on, turn it off, whatsoever, the output will stay at 0 until we gave the S input a pulse again and setting the output to 1. Now, in this case, a simple truth table might not be enough, because an input combination of, say, 0, 0 might not always give you the same output. Like, for example, RS is 0, 0 right now. The output could be a 0 or a 1 because it depends on if we gave R a shock or S a shock whatsoever. Now, meaning this mechanism has some sort of memory or state. This is where a state diagram becomes useful. Like you can see it on top of the screen, keeping track of the current state of the RS latch. In this case, we will make another video for state diagrams. Yeah. So
yep, just in case, if you guys just think, hey, I just want to play with logic gates, and just in case, we have it here. So in this case, this is LOwOgic Gate. So once you come over here, you can just go to the computer science room. Over there, we have a whole bunch of logic gates. The way you just pick one of them up. Like over here, we have the two parts, the main part and the emitter. So when you just hold the main part, if you just click it multiple times, you can just switch to different gates. However, here are some of the special ones. Like for example, this is the false gate. No matter what input it receives, it will always give you false. So if I click it and switch it to another one, this is the truth gate, meaning no matter what it receives, it will always give you true. And then the rest is just like, this is buffer A, buffer B, not A, not B, OR gate, AND gate, XOR gate, and then back to the false gate. So yeah, here we have it. If you have any questions, leave it in the comment section below. We'll answer it when we can. Yeah. So yeah, that's all the basic things that we need to know about logic gates. And yep, just like wrap things up before we end the video.
Yeah, so going back for the beginning of the video, the purpose of the logic gates are made for logical and arithmetic calculations in devices that involves with memory handling and memory optimization. The logic gates are very important in those sections of pretty much of hardware technology.
And then because if you just look at a single logic gate, it accepts input and then it gives you output, and therefore you can like think, hey, a single logic gate acts like a function.
And of course, logic gates are made from transistors. The three parts of the logic gate mimics a transistor. Of course, the input will be the collector, the gate itself will be the base, and the output is the emitter, which of course that leads on to the Boolean part of the Boolean function part of a logic gate. Of course, when a 0 is present, there will be no electrical current or no output that will come out of the logic gate. And of course, if there is electrical current coming out going into the gates, there will be electrical output. So for clarity, 0 will be no electrical current, 1 will be electrical current. The simple logic gates, we have three important building blocks of logic gates. You got your NOT gate, your OR gate, and your AND gate. NOT gate is pretty straightforward. It inverts any input it goes into it. It makes it into the opposite output. So you put a 0 into it, it'll output as a 1. Put a 1 into it, it'll become a 0. And the next second important simple gate, you got the OR gate, where if there's any input that represents a 1 input into the gate, it will always output a 1. And of course, if both inputs are 0, that means the output will be 0. And the third most important building block is the AND gate, which both inputs have to be 1 to be the output of 1. So for example, if you get 0, 1, that'll be 0. If you get 1, 0, that'll be 0. But if you get 1, 1, the output will be 1. These are the three most important building blocks, and they're always used in any logical circuit, no matter how simple or complex they are.
And just in case, from those three logic gates, we can build some other logic gates. Like for example, NAND gate is you just take an AND gate and then a NOT gate, and then for hash, you're done. A NOR gate, you just take an OR gate and you have a NOT gate, and then for push, you're done. Now, XOR in this case is beautiful, and yes, it can be built by using AND gate, NOT gate, and OR gate. But the basic idea of exclusive OR is if both inputs are different, then it will give you a 1. Or otherwise, if both inputs are the same, then it gives you a 0. So in this case, another way to see this, it's almost something like exclusive OR is like addition without carrying. It's like subtraction without borrowing. So we have that. And then another one is the not exclusive OR gate, which is easy. You just take the XOR gate and then the NOT gate for push. You're done.
And then we got the two more complicated circuits that we displayed earlier in the video. The first one being the full adder. So to go over the full adder which it grabs three inputs, which is use A, B, and your C in. and then it grabs those three inputs and would produce two outputs: the standard output, which is called the sum, and the second output, which is equals to C out. Of course, the C out is also known as majority once detector, whose output high goes more than one input, it will be logically added. It's full adder logic. It is designed that pretty much when 8 inputs are together, it could create pretty much a whole byte-wide adder and pretty much a cascade. Beautiful piece of circuitry technology. It's really good to help with just doing addition overall within circuits.
Yep. I would say, like, at the beginning, like when you're still like building logic gates, you only start from one side and every information goes from one side and flows into the other side. And things start to like become interesting when you start wrapping the wires back to its input. So that's what happened back at the RS latch or the reset set latch. So in this case, if you give a pulse at the set input, no matter what you do to the set input, afterwards the output will stay at 1. And then afterwards, if you give the R input a pulse, and then no matter how you mess it with the R input, you will force and set its state from a 1 to a 0. So in this case, like for example, if you play it a little bit more, you might realize that on an RS latch, the input may be the same, but based on its state, the output is different. Like for example, 0, 0 right now may give you a 0 right now, but maybe afterwards a 0, 0 may give you a 1. It depends on the state. So in this case, based on the different poles you give, it can like stay and switch in between different states. And RS latch becomes one of the fundamental parts when it comes to like making abstract machines. So yeah, we have it. Yay! So if you're watching this episode to the very end, thanks for watching, and I will see you in the next episode. Bye.
Bye.